Really briefly show you the other way of proving this. And it's always good to have more than one way to approach things. Not only does it mean you can use either, but you can also use them to verify each other in case it's not like a show, but it's like a find something, right? You can use both ways, and if you get the same thing on both, then that's got a pretty good chance you've done it right. Now, you might look at this, and it talks about distance between the roots, right? Now, if I call it k, that distance, you can immediately make some statements about the roots, right? So for instance, you might say, let the roots be, now traditionally we would call them alpha and beta, right, because there's two. But since I know that they are k units apart, I don't have to call them completely separate variables. I can call them alpha and, well, the other one would be alpha plus k, right? Because that's the distance between the roots. That's what I'm defining it as, okay? So now that I've got this, I can start to establish some things with it. So for instance, if you go sum of roots, okay, the sum of roots is 2 alpha plus k, right? And what is the sum of the roots equal to? It's minus b on a, right? Which is just minus b. And likewise, if you take the product, you're going to have alpha squared plus alpha k, and that's just equal to c. Okay. Now, keeping that in mind, how are you going to use that, right? Well, I want to now, I've worked out this part, and I want to go up to get that distance d in terms of all of this, okay? So how do I do that? Well, again, I'm going to say the axis of symmetry, right? It's just halfway between the roots, right? So it's halfway between here and here, it's just half of this, right? Does that make sense? So if I want to express it all in terms of alphas, because that's what I've got here, right? I'm going to have 2 alpha plus k on 2. So that's alpha plus k on 2, right? And I can take that and I can sub it into my original equation. That'll give me the y coordinate of the vertex, right? So what are we going to get? We're going to get y equals, that's x squared plus, now instead of saying b, I'm going to get it all in terms of alphas, okay? So this is going to become a minus, I think, yeah, minus 2 alpha plus k on 2 plus, that's what I've worked out to be c. Okay, I've got that in this line here. Right? Now, this is what makes this approach longer than the previous approach. You've got a bit of algebraic sort of wrangling to do. Okay, but sometimes, depending on the kind of question they give you, this approach will be the only one that works. The previous one, which is nice and neat, just won't be sufficient. Okay, so once you sort out all of your expansion, and you can see there's going to be a lot of like terms that cancel out. Okay, where you end up is just, well, yeah, there's a lot of cancelling. All the alphas actually cancel, okay? So there's like 2 or 3 lines here, you just have to be a little careful. But you can see, like say for instance, 2 alpha and k on 2, minus 2 alpha, k on 2. So what you're left with, 2's cancel, that's minus alpha k, and there's 1 over there. So you can see how all of the alphas will disappear. But this statement in itself, right, means that I can say d is the absolute value of that, right? And because I already know k squared is positive, I can get rid of, this, actually. Okay? Because that's what takes care of the absolute value, whether it be negative and that kind of thing. Sorry, I should have said k squared. All right, and that's already the statement. I'm already there, right? So d, at this point, is proportional to k squared. Okay, so as I've written it, it looks about the same length as the other one, but that's because I've skipped a bit of algebraic expansion here. Okay, but this is it's neat because it's using quite a different, theoretical approach. That's why it will work in different situations. Okay.